In this context, conformal field theories, which I will later focus on, are singled out as so-called fixed points under this renormalization group, so they are in a sense stable under this linking via the renormalization group, and they are specifically important to understand our phase transition and the so-called phenomenon of universality. Okay, and I added this kind of picture here to illustrate it a bit. So here in this picture, think of each of these hyperplanes as a given, each point in these hyperplanes as a given effective field theory, parametrized by some coupling constants. And the renormalization group is essentially some kind of dynamical system that links these effective theories between different scales. And what you want to do when you want to find a quantum field theory is, in a sense, take the limit under this iteration. And specifically, conformal field theories are like endpoints of these flow lines of the renormalization group. And more general QFTs are something like perturbations around these fixed points. So if you go a bit away from these points where the flow lines end. Okay, now let me come to the question of how to simulate quantum field theories, and there it has been, for example, pointed out by Preskill, I think in a nice review, that we should actually exploit this renormalization group paradigm. And what one would do, as we have heard in the previous talk, is simulate effective field theories relevant to a given energy scale. And in this talk, I want to think about these effective field theories essentially in terms of lattice field theories and finite volume. And there's been a lot of previous work pertaining, for example, to lattice gauge theories and Phi-4 theories and also fermionic theories in the sense of simulating such effective theories. And in this context, if you want, conformal field theories are especially challenging because they have no intrinsic length scale, because they are, in a sense, stable under this renormalization group flow. There's no natural mass scale or energy scale that is associated to this theory. So it's not so clear where to choose the lattice spacing, or how to choose it to get an effective description. So in this sense, it's vital for conformal field theories to understand what kind of error we make in simulating the models when we introduce such a discretization. Okay, and now the main idea for simulating conformal field theories and more generally quantum field theories in this talk is now that we should not only think about these effective field theories and simulating them, but we should also exploit the renormalization group flow to control the errors that arise when we discretize. That's in a sense the main point of this talk. If you want to take anything from the talk, then this is it. And the idea here, as was already mentioned in the previous talk, is that we have some quantities like correlation functions between observables A and B of a given effective theories, maybe evolved under some dynamics or symmetries, and we want to compare them to some continuum object. And that's the error we want to specify. And here I want to briefly mention that, of course, this error, in a sense, should be dependent on this dynamical parameter. Here, the actual discretization, which we are making, so the effective scale. But then there's also a kind of feature scale that is related to the observables A and B. So, since the scale these observables are sensitive to. And that's the thing which we want to exploit to approximate these errors. In a sense, we compare the feature scale to the actual discretization scale. Okay, and now let me try to make this a bit more precise for you. And for this, I've taken some inspiration from, let's say, constructive and algebraic quantum field theory, where people basically trying to use this formalism to mathematically construct such objects, such quantum field theories. And the formalism which I introduced with some co-authors, or a sequence of co-authors, is the so-called formalism of operator algebraic renormalization. And this formalism uses certain kind of input data, namely the first input data is a sequence of effective quantum systems. These are the effective lattice models, one for each given scale. And since we're working in operator algebraic setting, we think about Hilbert space on which a kind of basic set of fields and observables act, and we give ourselves an effective dynamics there. That's an input here. No? And then the second input is a sequence of initial states, which are sort of like approximating the vacuum state or some thermal state of your quantum field theory in the end. Yeah? And then the final ingredient are so-called RG channels, which describe how you change your observables from one scale to another. And that's the important physical input, if you want. And I think there's a kind of nice connection here with quantum information theory, because it's very natural to assume that these renormalization channels actually unitil completely positive maps. Yeah? And they are thought of in a sense as dual to so-called coarse graining operations. Yeah? I mean, if you ever heard about the renormalization group, then usually it's introduced in terms of coarse graining of states, and these RG channels here, they are the kind of operationally dual objects to these coarse graining operations. Yeah? And that's kind of mathematically technical thing which helps us to define what the quantum field theory actually should be in the end. Yeah? And this is illustrated by this next figure here. So this is a kind of mathematically precise version of this picture of the renormalization group, which I introduced before. Yeah, so let me first point out here in the right-hand side. So these are these algebras of observables or fields at different scales linked by the renormalization group. And under some mild conditions, you can take a so-called inductive limit of the system of algebras, which is essentially just a sequence of all observables under this linked by this renormalization group. Yeah? And that's a kind of basic set of observables of your quantum field theory in the end. Now, to get the renormalization group procedure going, what you do is you take your initial sequence of states, which is this diagonal here, and consider the pullbacks of your states at a given fine scale to a certain coarse scale, and thereby generate these horizontal sequences here. Yeah? And then the quantum field theory in this setting is nothing but finding the limit points of these horizontal sequences. Yeah? I mean, that's an actually very hard problem. Yeah? So, but that's the structure of the thing, and that allows us to make a precise statement of what it actually means to approximate the quantum field theory in terms of effective theories. Yeah? But a very nice thing is that once you have constructed these horizontal limits, then they are automatically consistent, and you can obtain this like double scaling limit if you want here, and the final quantum field theory will be given in terms of these two limiting objects here. So that's the thing we are after in a sense. And yeah, well, these ideas have been first, I think, pointed out by Zini and Wang in a paper from 2018. Then I have worked a lot in this idea with some my co-authors. And we have shown that basically for very simple models, we can really implement this strategy. Yeah? So for all the like standard quantum field theories, which you might think of, which are constructible, it's more or less possible to do this. Okay, and now let me come to a very specific implementation and talk a bit more about the conformal field theory aspect. And to this end, I want to consider certain type of 1+1 dimensional fermionic CFTs, which arise from a certain type of classic of effective models. And these effective models are essentially discrete spin models put on a circle of length 2L, and the Hamiltonian governing the dynamics at the effective scale is a kind of XY Hamiltonian with a certain transverse field. Yeah. And the initial states used in the construction of the conformal field theory associated to these effective models here are just the ground states of these Hamiltonians, which can be explicitly computed. So that's nice in this case. And let me also point out that these models are actually critical when this transverse field is vanishing here. So in the limit of the where we want to construct the conformal field theory, you should actually approach this critical point at a sufficiently fast rate when n goes to infinity, so to get to the conformal field theory. Okay, and now the important question I mean, one of the third ingredient for our construction is what are these RG channels, and the question is what are good RG channels here? And that's actually a design task. So it's not something that's just given by the mathematical formalism, but it should be informed by like the structure of the model. And probably you should ask your favorite physicist to tell you what is a good, good input here. And in these specific models, a good way is to use a good starting set of observables are the so-called Jordan-Wegener fermions, which I just wrote down here for, if you want to have the explicit formula. And we define these RG channels in terms of these basic observables. So as completely positive unital maps, actually they are just star morphisms in this case. And what we are doing here is essentially a kind of dual of a block spin transformation, but for the fermions. And means that at a given core scale n, we refine our observables into a linear combination of similar fermion observables at the finer scale. And this refinement is essentially expressed in terms of some coefficients, and it turns out that using here a low-pass filter from wavelet theory, which has also been done by some other authors, notably Evenly, White, and Brennan, I think, that this has some very nice mathematical features to actually control these maps in the end. I mean, so far as I understood, they basically use it for the states, so more for the coarse graining maps, but it's kind of dual version. But this is not the only choice we can make here. There are also other possibilities. We can do something like a momentum cutoff, which is more like the traditional thing in physics to do. Okay, but once we have this set up, then we can actually perform this limit here. Yeah, that's a kind of claim, but I don't have time. I'd like to show this to you. But given these ingredients here, so these effective models, these initial states, and this type of refining channels, we can actually compute these two objects and get the quantum scaling limit, which is then our effective field theory. And then you can directly check that the object you obtain in this case, once you're approaching the critical point fast enough, you actually get a conformal field theory. So in a sense, we are here now in a nice situation. We know that the limit is a conformal field theory. Now we can worry about how to actually approximate the conformal symmetries in terms of certain lattice quantities. And that's like the final thing I want to talk about. So are now conformal symmetries in this context and how to approximate them. And conformal symmetries are in a sense related to the energy momentum tensor, which basically generates local coordinate transformations. And in the CFT, we restrict ourselves to the conformal subgroup, which is then in a sense understood as those transformations arising from the two chiral parts of the energy momentum tensor. And a typical way to deal with these conformal transformations is to consider the conformal generators, which are essentially the Fourier transformed versions of these, or the Fourier modes of these energy momentum tensors. Okay, thanks. And now an approximation on the lattice scale, on the lattice can actually be achieved in the following way. Namely, we observe that the 0,0 component of the energy momentum tensor is nothing but the Hamiltonian density, which is expressed as a linear combination of the two chiral parts of the energy momentum tensor. And this is used as the basic formula to extract approximants for these objects. Yeah? So to in the end get approximants for these conformal generators. And there's a formula proposed by Ku and Saleur, where you take first the Fourier transforms on the lattice of the lattice Hamiltonian density, then you have a kind of complicated formula for the lattice approximation of these conformal generators. And these objects here, they should approximate the continuum conformal generators in a certain sense. And this sense, I wrote down in which sense this is done, and that again uses the renormalization group in terms of these RG channels, in the sense that you compare the action of the conformal generators at a certain scale, at a certain coarse scale, with the action of the conformal generators at a given finer scale. And then you have to perform essentially this double limit by first pushing out the simulation scale, or the effective scale, if you want, n, and then also taking the limit over this comparison scale m here. And we have shown in this two publications, which are the basis for this talk, that this is actually correct. Yeah? So this approximation result holds true for these conformal generators in that setting, using these refinement channels which I introduced. Okay, and now, well, let me basically conclude with the main approximation result, which I state here as a kind of meta theorem. So we have for arbitrary observation scale m, okay, that the difference between these effective correlation, dynamical correlation functions, where this dynamical transformation of one of the observables is not only like the Hamiltonian transformation, but it can be any conformal transformation of the observable B. If you compare this to the actual object in the continuum, then you make a certain error, and we can show that this error goes to 0 if we send the simulation scale, so this n here, the effective scale, to infinity, and it does so uniformly in T, in compact intervals of the symmetry parameter. And there's also another nice observation, namely that in certain cases this error scales quite nicely. So it depends, of course, on the observables A and B, but it goes essentially like with the inverse of the squared inverse of the simulation scale. So if you double your lattice, you get 4 times better simulation. And finally, let me point out that if you do this just for kind of one particle states, so where these A and B are essentially fermion operators that generate one particle states, and you sandwich in between them, for example, a generator of a conformal transformation, then you get already very good approximations. Yeah. Okay. So then you can already get quite good approximations with only a few qubits if your observation scale is not too far away from the unit scale. Okay, that's